Hello, everyone. My name is Chunyuan. I'll continue to discuss the topic of vision language pre-training for the core computer vision problems. You have learned from DMA about how to do VLP for image classification and learned from Punchan how to do VLP for object detection. In this talk, we are still solving the same set of computer vision problems, but we shift the angle a little bit by focusing on two specific topics. One is internal knowledge, and the other one is benchmark. Let's start by reviewing the existing research and current trend. Zero-shot learning has been studied for at least 1 decade in our computer vision community. Most of the research have been focusing on building models to generalize to unseen object categories or classes. I would call this traditional setup as zero-shot learning in the class level transfer setting. Thanks to the recent advances in the VLP, we have observed a clear trend that moving from class level transfer to the task level transfer. For example, CLIP, it trains on the web scale image text data and then evaluate the model performance on over 30 image classification data set. For class level for the class level transfer, we have a very rich line of research in the community. For example, I think the key of this live research is trying to using some type of auxiliary information. For example, we use the implicit knowledge from the pre-trained model. We have also used the explicit knowledge from knowledge bases. But how to generalize the idea of external knowledge from the class level transfer to the task level transfer, as that is not studied before. And in this session, I'll show our recent attempt to generalize the idea to the task level. I'll talk about the K-Lite. And for the second topic, benchmarking. And in our community, there are several data sets designed specifically for the class level zero-shot learning evaluation. But how to do the task level evaluation for these zero-shot models, and this has been a very challenging problem in the community. And we are in this talk, I'll also briefly talk about our effort trying to tackle this problem. Okay, the first part, how can we train a generic visual backbone by leveraging external knowledge? So let me start with a motivating example. Leveraging external knowledge is actually a very common approach for us human beings to use to make visual recognition decisions in our daily life. Imagine the first time we are in a Japanese restaurant and we are offered a menu with different dish names only, and it's very hard for us to understand what they are, not to mention to recall the visual appearance of these dishes. After the waitress explains the concept using her knowledge, we may immediately have a better idea of the dish, and then we can order the correct dish we have imagined. You have seen that for our human beings, instead of trying to memorize all the concepts, we humans actually to leverage some type of structured knowledge to efficiently adapt it to new settings and new domains. And similarly, we are asking a question, can we borrow the idea from machine learning? And as external knowledge is generally available in different domains, for example, we often have some domain-specific data sets or some textbook or instructions. Can we treat them as external knowledge and trying to build a systematic and generic approach to leverage this external knowledge for the task level transfer? So K-Lite is a recent effort we have tried to leverage external knowledge for vision language learning. So in the previous talk, we have learned that most VLP models, they are trained with image text pairs. And this is the baseline we are considering in this project. In the K-Lite, the language side will be enriched with external knowledge. It first construct queries using some entity extraction technique, and then we will use the queries to query the database, and then we get the corresponding external knowledge for this concept. So we can then use this retrieved external knowledge as an additional supervision for the image language learning. So the same now we can see that with K-Lite we are actually learning using a full data spectrum that include image, language, and knowledge. While in the traditional setting, we are only leveraging image and text. So we will apply this knowledge augmentation process to both the training stage and the evaluation stage. So let's use this sashimi as one example. And we see that external knowledge provides rich semantics and sometimes common sense to explain the concept. In this example, we see that sashimi has been explained with its hierarchical information or the shape information. So we will apply this K-Lite into two hardcore machine learning computer vision problems. One is image classification. We are trying to leverage external knowledge for UniCell for the task level transfer for image classification. And in the second setting, we will apply K-Lite to the glyph setting, where we pre-train on a large object detection data set or image language data set. Then we're trying to see how it improves the task level object detection transfer. Let's look at the result on image classification first. We use UniCell and the baseline pre-training method for those who are not familiar with the context. So scaling on UniCell leading to the Microsoft Florence model, which has outperformed the glyph in many computer vision problems. So in our controlled setting, we evaluate the model for its zero-shot and few-shot performance on ImageNet and 20 image classification data sets in the downstream. And the average score are reported here. So we see that K-Lite is more sample efficient than UniCell. For example, it shows that the K-Lite has shown comparable performance with UniCell using only a half number of training image text pairs. We also we provide the breakdown analysis results, and it shows that K-Lite improves zero-shot learning performance on 17 out of 20 image classification datasets. And first of all, we take out the top two datasets that external knowledge benefits the most. It turns out those are the fine-grained image classification datasets. This makes sense because oftentimes for this dataset, we have the so-called real concept, and external knowledge provide descriptions for this concept, such as the color information or the shape information, and therefore it converts the real concept into more common concept or words. And second, we also look at in which cases external knowledge actually hurts the model performance. It turns out it hurts the model performance when the quality of the knowledge is low, or the external knowledge contains some words that confuse the model. So we also apply the technique to object detection, and roughly speaking, we see that it improves a simple glyph model on both Z-based dataset and 13 downstream object detection dataset in terms of zero-shot task transfer learning performance. So then I'll quickly move to the second part of the topic. how to do benchmarking for the task level transferring. So this is a more challenge and a topic for our community. Specifically, I'll talk about our recent effort called Elevator, which is a benchmark that when I introduce the talk, I'll briefly mention the related efforts in our community. So as we have showed in our tutorial, image classification and object detection are two important tasks in computer vision. And with deep learning, and the community has reached great results on some standard data sets, for example, Internet and COCO. However, in real-world scenarios, there are many more interesting visual recognition tasks. For example, now we are attending CVPR at New Orleans this time, and we must be doing a lot of novel food recognition problems when exploring the city. We are also dealing with COVID-19, and this creates a new scenario. For example, the detection of wearing mask. So all of these are interesting new computer vision problems in the world. So a good model that performs well on Internet or COCO does not necessarily performs well on those new interesting computer vision problems in the world. So with recent language augmented visual models such as CLIP, we have seen the opportunity to build such computer vision problems that can easily transfer to a lot of downstream computer vision problems. And for example, in many of our tutorial sessions today, we have seen models, right? And they are achieving the so-called better and better performance. But are we really making solid progress? I think this is a question mark, because oftentimes people reporting results on a subset of these tasks. So sometimes, and even when we read the paper carefully, and we don't see the details how the model is actually adapted to the new setting. I think all of these hidden details prevent the community to build a fair and transparent benchmark to making a solid progress. So now I'm going to introduce our benchmark Elevator. In terms of data, we collected 20 image classification data sets and 35 object detection data sets, and they are public data sets. They representing either the academic setting or the real-world settings. For a new task in the wild, as humans, we often trying to add some customized specification or note to trying to clarify the task. For example, we may add some explanation or the attributes of a visual concept to tell others or to tell the model what the task really is. So to mimic this spirit, we add external knowledge to all the visual concepts in our data set. This included WordNet knowledge, Wiktionary knowledge, and GPT-3 knowledge. And all of this knowledge, they provide richer semantics in the form of natural language, explain the concept in different ways. Now we can review and compare different benchmarks. In this table, most existing data sets, they are designed for the traditional class level zero-shot image classification problems. And WeTab was a data set, a benchmark introduced by Google. It aims to evaluate the task level transfer, but the benchmark is language-free. Therefore, the benchmark cannot be used for zero-shot evaluation. And Lewis is another long-tail object detection data set. Comparing with them, the Elevator benchmark covers many task domains and is enriched by external knowledge and allows the task level transfer with any number of training examples. So we further visualize and compare the task diversity. ImageNet and Lewis are well-known computer vision data sets. We visualize the semantic space using 2D PCA, and they have both data sets, they have rich visual concept, but they relatively concentrate in a subspace. In contrast, our CV involved data sets in the elevator, they are collected from many different applications and different domains, and they are more diversely distributed in the same semantic space, and can better represent the full task space for computer vision involved. Even we can simply compute the standard deviation or STD for these semantic points for different benchmark. We say that the elevator benchmark contains a higher diversity score. It means that the tasks we cover are more diverse. I'll then talk about another contribution of this benchmark, which is Toolkit. And we know that in the previous study, Toolkit is hidden, right? It's not provided, and it requires a lot of effort to develop software toolkit so that you can reproduce somewhere else algorithm. So in our toolkit, we have two major components. The first one is automatic. The first one is automatic hyperparameter tuning strategies. This includes learning rate and rate decay. You don't have to tune your best hyperparameters for each single data set because it requires a lot of effort. And our toolkit will help you to get your best hyperparameters for a specific model and a specific data set. And the second component of the toolkit is the language-augmented model adaptation method. So when CLIP was proposed, the authors follow the tradition in the computer vision community by randomly initialize a linear head and then train the linear head for a specific data set. And this random initialized method for the linear head is a suboptimal solution. And because it only leverages a part of the pre-training power, we can say that the pre-trained text encoder is not used in the random initialization method. And instead of that, we are trying to leverage the full power of the vision language pre-training models. And so specifically, we propose a simple method called language initialized adaptation method. And so the basic idea is to initialize the linear head using the output of the language encoder. So now let's take a look at the performance for this language initialization method. So we are comparing in both linear probing and fine-tuning setting for different number of training examples. The proposed language initialization in our toolkit outperformed the baseline random initialization significantly, especially for the few shot learning setting. And we show that even with very few shots, for example, one shot or two shots, in both linear probing and fine-tuning setting, the proposed adaptation method is better than zero-shot CLIP. But this is contradictory to the original CLIP paper. They show that zero-shot learning is better than few-shot learning. For example, we need a four-shot to get a better performance than zero-shot. With this proposed language initialization method, one can also ensure that few-shot is always better than zero-shot for vision language models, because you can imagine that the zero iteration of our algorithm actually reduced to the original zero-shot evaluation setting. We also report many baseline results. So even though our benchmark is originally designed for VLP models, but nothing stops us to evaluate any pre-trained vision models and use them as baseline. Specifically, we consider several mainstream models. This includes self-supervised learning method, for example, MOCO and MAE, And we also include the self-supervised learning method, for example, DEIT and VLP. And we are using a slightly different taxonomy, and we call the self-supervised learning and the supervised learning as language-free visual models, because in their pre-training, no language information is used at all. Meanwhile, in this benchmark, we focus on evaluating the models that are pre-trained with language information. So now we can take a look at the result. We are reporting the average results for 20 image classification data set under different number of training examples. And surprisingly, we found that the model performance ranks differently than some of the previous reported results. And we see that MAE is actually worse than MOCO V3. And self-supervised learning method is worse than supervised learning method. And it turns out language image training pre-training method such as CLIP performs the best. So note that our conclusion is obtained using the automatic hyperparameter tuning method and a very simple data augmentation method. And the same automatic tuning process is applied to all the model checkpoints. And this is different from the original papers that they often try to propose some advanced fine-tuning method or some advanced data augmentation method so that they can get the best performance for their pre-trained models. To encourage DNI for our research community, we encourage people to report the results in two different tracks. The first one is industry track. It aims to evaluating the scaling success of models and data, as long as the downstream data sets are not used in the pre-training. And second one is the academic track. And it has a fixed pre-training data set, which is limited to public and established data set. And it aims to encourage innovations of research ideas and methods. By benchmarking different pre-trained methods, we see that language-augmented visual models is performing better than the language-free models for two reasons. First, of course, we get a better final recognition accuracy. And second is VLP models actually enable zero-shot transfer, while the traditional language-free models, they cannot do this. I'll also recommend the 3 different playgrounds based on this benchmark and to accommodate different research efforts in our community. So the first one is sample efficiency. So a good model should also be able to achieve good performance with a smaller number of training examples. And we recommend to use zero-shot and few-shot as a quick and cheap approach to evaluate the model performance. This is especially for the teams with limited computer resource. And I think zero-shot and few-shot are enough to evaluate the quality of the pre-trained model. And these are also the settings that the pre-trained model can benefit the most. There are also some other VLP models developed in our research community and mentioned previously in our tutorial. And it will be very valuable if all of the benchmark, all of the pre-trained model can report the result on a fixed set of task data set so that we know that we are making progress. And the second one is parameter efficiency. So a good model should also be able to achieve good performance with a smaller number of trainable parameters, because this typically means that training efficiency. In general, as expected, a larger number of trainable parameters often leads to better recognition accuracy in many settings. And most of the so-called parameter efficient method is playing a trade-off game between the number of parameters and the model performance. And in our study, we recommend to use few-shot learning as a setting to study the parameter efficient method. because this is a more interesting setting where the best performance actually requires an optimal number of trainable parameters, not the largest number of trainable parameters. And inspired by NLP, and there are many parameter efficient model adaptation method proposed recently for VLP models, and it would be valuable to report results on a fixed data set and a diverse data set, such as elevator, so that we can be convinced that the adapting method is sample efficient. And the last part is, the last playground is to study the benefit of external knowledge in an open domain setting. In general, the knowledge can be viewed as a new type of language prompting technique. And let me illustrate this in two cases. And the first one is using a language augmented pre-training method, such as K-Lite. And we observe that adding Wiktionary and GPT-3 knowledge can actually improve the performance. And in the second case, we are considering a knowledge-free pre-training checkpoint, for example, CLIP. And we see that adding external knowledge can improve both the few shot and the few shot model adaptation results for CLIP. And these are very simple baseline methods. Based on this, I hope that it can encourage more advanced knowledge-aware prompting techniques in the research community. And finally, we are organizing an ECC workshop and challenge to encourage research to develop computer vision models that can easily transfer to a large number of downstream applications in the world. And the benchmark and toolkits are also released. And let us know if you have any questions. And then we will go to our last session, moving to text-to-image generation. Thank you.